I'd like to talk about a different way to think about least squares that's very useful for conceptualizing what it's doing. So imagine our y is a 3 by 1 vector and our x is a 3 by 2 matrix. So we only have 3 data points and we're going to try to explain them with 2 predictors. I agree, not a terribly useful scenario, but because I can only draw this in 3 dimensions, that's the best we can do. But hopefully you can use this to think use it to reorganize how you think about least squares. And we want to minimize y minus x beta squared. So let me define by gamma equal to the space of x beta such that beta is in R2. So what we want to do is minimize y minus y hat squared where over the collection of y hats that live in gamma. So let's draw a picture. Here's our 3 dimensions for our 3 data points. And our point y is a vector in this space. So now think about this space gamma. It's indexed by a 2-dimensional parameter. So it is a 2-dimensional space. We're drawing it in 3-dimensional space and it's linear, so it's going to be a plane. So this looks like a plane, and that's gamma. So what is y hat? So actually, let me rewrite this earlier statement a little bit by calling it y minus z for z in gamma, and let y hat to be the actual minimizer of that equation. Okay, so what is y hat? Well, it's the point that minimizes the distance between y and points in this plane. So it's the point in this plane that's minimally distant to y. So it's the orthogonal projection onto the plane. So let's draw it like that. Here's our orthogonal projection, and there's y hat. So y hat is the point in gamma that is minimum distance to y. So thinking about it this way really kind of helps us think about different aspects of how we apply multivariable regression. For one thing, notice that if we include a redundant column in X, if we include an extra column in X, say X was the vectors x1, x2, and then the completely redundant column x1 plus x2, okay, we'd see the rank of that matrix is of course still 2, but notice that the space gamma, let's call this, I don't know, I'll call that x prime. Well, no, x prime is going to be like transpose. Let's call that x tilde. Okay, so the space gamma tilde, which is equal to x tilde beta such that beta is in R3, that space, you can prove to yourself, though I think it's pretty easy to see, is identically equal to gamma. Because, if we take a linear combination of x1 and x2, we take the collection of all possible linear combinations of x1 and x2, that's the same thing as the collection of all possible linear combinations of x1, x2, and x1 plus x2. So what we see is that we don't actually need an invertible matrix to do regression. We just need the space defined by a linear independent subset of the collection of columns of X. That's an important point. So at any rate, so it also tells you that if you have, let's say, let me give you an example. If you have an X that includes an intercept and a vector that's 1s for a while and then 0s for a while, right? And then consider another X that's 1s for a while, and then 0s for a while, and then 0s for a while, and then 1s for a while. and then consider another x, which is 1s, and then 0s, and then 1s. Okay? Notice these two add up to a vector of 1s. So all three of these cases are identical. They all have the same column space. Okay? So in every one of these cases, the gamma, the space defined by linear combinations of the columns of these design matrices is identical. So the y hat defined by these design matrices will all be the same. Okay, so that's an important point. Okay, so our y hat is the projection of y onto the space defined by linear combinations of the columns of x. That also means, because we know what the solution is, beta hat, which is the particular, which is x transpose x inverse x transpose y, that is the particular vector in R2 that converts x into the correct set of its linear combinations of its columns to form the projection. So our y hat, our projection, is x transpose x inverse x transpose y, which I've been using H to refer to this matrix, H of x. So it is interesting to note that the linear operator that takes a vector z and moves it to H of x times z is the operation that projects a vector in Rn onto the two-dimensional space spanned by the columns of x. So H of x is exactly a projection vector. It's a projection operator. So it's often called the projection matrix. Sometimes it's also called, the reason I give it the letter H is it's often called the hat matrix as well. The final thing I'd like to point out is if we consider our residuals, that's the points E equal to y minus y hat. Okay, so that's y minus x transpose x inverse x transpose y, which we can also write out as I minus the hat matrix times y. So notice our residual is exactly the difference between y and y hat. So that's this vector right here. That's E. So, if we write it over there, that's E. But notice that E is going to be orthogonal to any point in gamma, right? So E is going to be orthogonal to any point in gamma. And what does that mean? That means E transpose times Z has to equal 0 whenever Z is equal to x gamma for some gamma. Okay? And in particular, our residuals are orthogonal to any column of x, and we'll elaborate on that point here in a minute. But let's actually prove this mathematically. We can see it geometrically pretty easily, but let's prove it mathematically. Well, we've mentioned this in previous lectures that if I take I minus h of x and I multiply it times x, I get 0. So certainly if I multiply it times x times gamma, that is also going to get 0. So you can go through, if you didn't see this in a previous lecture, just actually go through it. It's a very easy thing to prove. And so that's showing, again, that the residuals are orthogonal to every point in the space gamma. So this means that if our x contains a vector jn, intercept, and then other columns, this means that E transpose times jn has to equal 0, which means that the sum of our residuals has to be 0. But it's not just that the sum of the residuals have to be 0, it's E transpose times xk for any xk column of x also has to be 0, or any linear combination of the columns of x also has to be 0. Okay, so the point I wanted to get across in this lecture is that it's quite useful to think about geometry and geometrically what's occurring when you think about least squares. Often this will help you logic your way through actual applied statistical problems if you can think about these problems geometrically.